Thank you. So where are my slides? Command. Easy. Peter knows all the tricks. Okay. So today I'm going to talk to you about lively data. So I hope everybody is feeling lively and wide awake. I'll introduce myself, although I guess I just got some of it. I'm now working as a sales engineer at Google. I've been there for 2 months, so I'm a noodler, and I've done two main things. So they gave me a funny hat with a propeller on it, and they sent me to Mountain View so I could try out that really cool slide. And also I learned about some really great technologies since I started. So that's what I want to do today. I want to show you a demo that involves some of the things that I think are cool that I've seen in the last 2 months. When I got to Google, I discovered that we've been a cloud company for a very long time. Yeah, maybe some of you have used Google Cloud. But way back in 2002, we were already publishing research papers on things like Google File System, and then I'm sure many of you, who's into big data here? It'd be interesting to see a show of hands on that. So quite a few people, yeah. So in 2004, we published a paper on MapReduce, and I think this is a series of big data technologies, and we have this history of innovation. And we publish these papers, and then open source packages build on some of the ideas there. And there are a few things here which could be a talk on their own. So I'm going to move on. I'm going to talk to you about taxis in New York City. So I want to set the context a bit. The taxis in New York City have interactive advertising screens in them. So I don't know if anyone's ever been in one. I haven't, but the passengers can interact with ads while they're driving along. And what we want to get to here is a way of targeting relevant advertising to people according to where they're going, based on a really nice big data set that was contributed by the New York City Taxi Commission. So they had information on 1.1 billion, I think, taxi rides. And Google took that data for the sake of a code lab, which you can all find on the internet. And it extended it to add route data. So we had the start point and the end point, pick up and drop off point of every taxi ride that happened in New York City for quite a long time. And so that extrapolated data makes for a really nice simulation. And we've got things like the time that the pickup happened, where it happened in latitude and longitude, the drop off, and we've added to that clickstream data for the ads that the users are interacting with, or the users. I'm always thinking about computers, but the passengers, I guess, or the riders. So I've got to push a few buttons now, and I'm going to get some lively data on the screen. So bear with me. So what I'm doing now is I'm connecting up a messaging system called PubSub directly to this visualization. And it looks really nice, doesn't it? So over there you can see Manhattan, which is where the dense area is, and you can see that New York's, I think there are 3 major airports. So there's LaGuardia, and there's JFK, and there's Newark. So that's why you see those sort of arteries of traffic, taxi traffic flowing. And we want to get to the point where we can build some sort of recommendation system so that we get relevant ads, because there's no way you want to be recommending, say, a restaurant that's not even on the route. And you might want to recommend, for instance, according to the number of people in the car, or what you think the person might want to do when they get to their destination. Something that's happening here is we've just connected this up. I think I can show you now. This is something called data flow. So it's a bit of a shame that the text is gray, but the data coming in, what is it saying now? We're dealing with about 10,500 events per second. So we're getting every bit of telemetry that the taxi sends, or the simulated taxi, in real time, and we're pumping it straight into a Chrome browser, which is just pulling messages by HTTP from that queue. So it's totally overwhelmed. So what we need to do with that pipeline is find some way of condensing the data so that it can keep up. Because right now we could look at a graph that would show that our backlog of messages is accumulating, and we're just not processing stuff. I think here we're dealing in the browser with between 3,000 and 4,000 data points per second. So we can do things in this pipeline with a technology called data flow to try and get that down. So back to the slides. Here's the architecture that we need to get to condense that data. Something we want to do, you see historical data there, as well as getting a sensible visualization. We want to have a historical archive, so something that an analyst can look at, perhaps in the case of, say, a financial thing, say we're dealing with fare data, how much the user's paying. We need to make sure that we have a totally accurate and reliable backlog of everything that happened. And we might not care how long, that could eventually be resolved the same evening as the taxi ride, so hours later. But the visualization, we need lively data. So we've got two sort of competing use cases to deal with. And what I want to show you is, to get to the recommendations, we could take a rule-based approach. So we've heard some interesting talk about recommenders today. So that archive is going to a product called BigQuery, which is an analytical data warehouse. Google has customers who are making queries over trillions of rows, petabytes of data, and there's a lot of data in this. It's been building up since just before I started speaking. So we could run a query that's something like this. So the analyst is looking for an insight. We're interested in knowing about taxis that are going to a place called the Upper East Side in Manhattan and are originating from airports. So we've just put a where clause here in our query to say, to put bounding boxes of latitude around certain areas of the map, and say if our pickup destination is in this box and our destination is in this box, then we've got an airport ride. Otherwise, it's something else. So if I think I can run this query now. And it's pretty much standard SQL that we're running here. And it's going to take a few seconds to run, and it should tell me quite a few seconds. I guess I ran that. Yeah, so we just processed 266 gigabytes of data. And we found out that we have roughly 14% of our taxi rides going to the Upper East Side are originating from airports. So we've learned something here, but can you imagine trying to establish a rule like that for every possible scenario that we wanted to build into our recommender? I think we can all imagine it's probably not the best and most scalable approach we could take. So we need to think of something else. So back to the slides. And that would be perhaps machine learning or applying some more complex model. And I think originally someone suggested that I might actually give a talk on TensorFlow today, but I thought that was a bit of a tall order 2 months in, although I'm learning about it, and it's a fantastic thing. So TensorFlow is Google's open source library for machine learning. And has anyone, who here hasn't heard of TensorFlow? I guess roughly half of the people, maybe? Yeah, interesting. Well, it has 53,000 stars on GitHub, the open source project repository, which makes it the most popular open source project for machine learning. And I'm not going to dive into the depth as I suggested, but what we thought worked well here would be what's called a wide and a deep model. So we have a linear recommender, which was talked about earlier. It's something that's good at memorization. So it memorizes lots of rules. So I don't know, like a taxi going to the airport, people might be interested in buying a certain product there, presents to take home with them, or a taxi going into the city from the airport with 3 people in it, or with multiple people in it, might be interested in seeing a show on Broadway. And at the same time, we can have another kind of model called a deep model, or a deep neural network, which is very good at generalization. So I guess you could say it might learn about things that are in the same space as other things that people like. And TensorFlow basically gives us a nice API, a high-level estimator API, to train a model that can understand, that can deal with both things and generate estimations which take into account both types of rules. And it's quite an appropriate thing for recommending advertising. And then we can deploy that model on a cloud service, or not just deploy it. I say we can actually train that model on the cloud machine learning engine. And once we've deployed it, once we've tested it and trained it and done the research, we can pretty much instantly put it into production, generating predictions at scale. So there isn't this disconnect between when you train your model and then deploy it, where before you might have to take something, you learn something great about how to write a recommender or an estimator, and then you have to kind of rewrite it to get it into production. But TensorFlow makes it easy to deploy a model in production on, say, something like Cloud Machine Learning Engine, but it will run on an iPhone or an Android device as well. So here's the architecture we want to get to. The idea is that now, as well as doing the archive and condensing the data to make it good for a dashboard, we want to generate recommendations. So we have trained a model, and then we run it in production to serve suggestions for the advertising. Now, what took me to this, I said I was going to talk about streaming data, is we need some sort of glue to tie all this sort of stuff together. So you saw the nice graph with the data coming in at an extremely high rate. We need to think about some of the things that I really struggled with in my previous jobs dealing with streaming data. We need to think about how we deal with both batch data and, like the thing I talked about before, about having an archive for an analyst which has to be complete and accurate, and then a lively visualization. And there's this great SDK called Apache Beam, which was donated by Google beginning of last year, which makes it easy to reason about batch and streaming data. The Beam is the SDK, and Dataflow is the runtime engine, but you could also run Apache Beam on Spark or Apache Flink, another runtime engine. This is an example of deploying it on Google Dataflow. So what happens is it's basically like MapReduce, but the details of how you do your MapReduce, distributing your workload across lots of different computers, because the data is so big that it doesn't actually fit on any single computer, is now separated from your code, so that runtime information doesn't leak into the code and pollute it. You can really just focus on the things you want to do, like aggregating data, counting, working out top end, and that kind of thing. And Cloud Dataflow or the other runtimes will take care of starting up the virtual machines, dealing with dynamic job rebalancing, storage. If a machine falls over, it will automatically recover from a checkpoint so you don't lose data. All of those kind of things. You can even update a running pipeline with new code. So a bit of the history of Apache Beam. I mentioned that MapReduce paper back in 2004. We published that MapReduce paper, but we didn't publish any particular frameworks. And we had a history of publishing research papers and leaving them for the community, and building our own services based on that research. That ended up with Cloud Dataflow. And then leaving it to the open source community to build tools. You recognize some of the major ones, the data science people like Hadoop and Spark and HBase, and all of those extremely popular open source tools for dealing with big data. And now there's Apache Beam, which aims to bring that research and that runtime engine, and also provide connectors for all those great open source tools. So that's why it was contributed. Does anyone remember something called the Lambda Architecture? So the idea here was that you had to deal with this lively data and this batch accurate data, And the suggestion was that you should just build two separate infrastructures effectively. So something to do with the fast stuff for the visualization, and then Hadoop, say, MapReduce for the batch job. And that was kind of expensive in both brain time and infrastructure, because you really had to do everything twice and then reconcile that. So what we aim to do with Apache Beam is to provide a unified model over both batch and streaming data. And by streaming data, I just mean data that just never stops coming. So you never know when you're finished processing it. And what Beam and Dataflow are basically a framework and an engine built for streaming data that also supports batch, which is significant. Now's the right time, so that those messages are all coming in on PubSub, something called PubSub. It's a many-to-many messaging system. That's how we're getting in our 14,000 to 18,000 messages per second. And any people who've dealt with distributed messaging know that there's a problem, perhaps, that you always have to make trade-offs. So the guarantee you get from PubSub is that every message will be delivered at least once, which implies that they might be delivered twice. And also, they don't necessarily get delivered in order, first in, first out. And that's the point where I used to panic, when I would think, how am I going to deal with infinite out-of-order data? And the tools I had available to me in my old jobs didn't really solve that problem for me. But Dataflow gives us an answer here, and I think it's a really nice one. So I wanted to talk a bit about how it does that. So here what we have is the concept of event time. So these events all happened at 8 a.m., but also processing time. So the two over on the left arrived soon after they actually happened, but this one here arrived many hours later. So an example might be something like a computer game where you're computing high scores and the person's on a plane and they have airplane mode on, and then later on when they get off the plane, they turn off airplane mode and it syncs, and then this event gets delivered hours later, but you might still need to compute something based on it and tie it together with the other events that came in. So we have this concept of event time and processing time, and that's what you can see on this graph here. So event time is when the thing actually happened, and processing time is when our system got to deal with it. So you have this ideal line here where events can be processed no sooner than that. Processing time equal to event time. So 1, 8, and 3 are more or less arriving on time, but you can never have anything on the other side of the line, or else it would defy the laws of physics, I guess. So 3 was nice and on time. 9 was seriously late, and we need a way to think about that. And this sort of stuff was really difficult before I ran into this. So Beam asks these 4 questions. It's asking, what are we calculating? So are we doing aggregations? Are we calculating top n? Are we summing things, counting things? We ask ourselves, where in event time? So are these results calculated? So for our visualization, we need to just get stuff on the screen pretty quickly. And when in processing time are those results materialize? Those are closely tied together. And then how do we deal with refinements, which basically means that late data, that number 9 on the previous slide. So this is probably things that people who've done MapReduce realized before. This is just what we're doing. So here we're adding up some numbers. We're adding up, say, high scores. That's the what. And we deal with parallel collections, never-ending collections, effectively, and parallel functions. And this is what is happening. So here we're counting the high score. The number, this graph's not complex. The number we're calculating is the high score, the sum of all the scores that have come in at all these different times for different games, and working out a combined total, and we get to this number, 51. But over that 9-minute period, we had to, of event time, we had to wait 10 minutes until 12:10 before we could actually broadcast that result and use it. So this is a classic batch processing model. You have to wait for everything to be there before you can generate the numbers, which doesn't work in a simulation or a visualization. So one way you could deal with that is to break event time up into windows. That's the where. So let's say we divide the time that events are coming in, because they're coming in forever. So in the extreme case, you would have to wait forever to get all your events together. So here we say, well, let's just chop it up into windows of 2 minutes and work out the sum for each of those windows. So then you end up with something more like this. We just get a nicely aggregated sum for every 2-minute period. But we still have to wait for all the data to be there. So we can talk about when in processing time. So this is about perhaps when are we going to stop counting and do something and tell our end systems that it's time to actually use this data for something. So we can trigger, and there's this concept of the watermark, which just means that the system is working out roughly when it thinks it should have received all the events for that window. And it calculates a watermark, a heuristic, and triggers and sends out the number. So then we get this. The green line represents the watermark in event/processing time. But we still have a problem, because we see that our number 9, our favorite number 9, has arrived late. And ultimately, we need to be able to deal with that if we want to have something like an accounting system or something totally reliable. So we get to the thing about how to do refinements, and there's more code here. So this is just saying that we fire early. So every minute we send what data we've got. And if we get something a bit later, just one thing a bit later, we fire again and let that information out, and we accumulate it. So we just add it on to what we've already got. So then you get it something on time, is submitting stuff early, and then finally it emits early several times, and then finally we get the late number 9, and we can make an adjustment or whatever it is we might want to do with it. So we've got these 4 different models for dealing with things. Sometimes batch is fine, or windowed batch, and we've got all these powerful ways of reasoning about streaming data. And it might seem simple having said it like that, but I guess people have dealt with quite complex streaming problems, even just counting clickstream data and needing to serve up results or recommendations to users. And we also have, I showed the fixed windows. We have the ability to do fixed windows or sliding windows for a visualization, or even sessions. So sessions are interesting because in our taxi rides, we have the concept of a ride, and every event that comes in is a ride ID. And we need to emit our data early, but we also have the concept that the ride's over. But we don't know when it's going to be over necessarily, so we use session windows with early firing to say, if nothing happens for 5 minutes, that's the end of the session. So in the case of session windowing, it's really dependent on the data. So here we've seen that we're using PubSub to ingest our data at scale. Dataflow is the system that brings the analytics pipeline together. It's the glue, and that's the thing that I was really impressed by. BigQuery for an archival data warehouse to get completely accurate data over all time, and a machine learning model. So I'm going to go back to the demo now, and we can see that Chrome has been completely overwhelmed meanwhile. So that's because it was connected to the fire hose. So what I'm going to do is connect it up to the condensed stream of data and start fetching some rides. And meanwhile, let's have a look to see what we're dealing with. It's down to 4,500 elements per second. So I think it's dealt with a backlog it built up when it started. And here we have some ride data. So I think I can show you some. Let's pick a taxi in Manhattan somewhere. And we can say that this we can see that this taxi is en route from one place in Manhattan to another place in Manhattan. It's got one passenger in it, and our machine learning engine has mixed into the data stream some predictions, and it's recommended somewhere in Manhattan to have breakfast, which seems pretty relevant. Or we could try another Manhattan. Well, this is not real, right? Wouldn't it be nice if we actually had a real feed of all the New York taxis? Yeah. Yeah. So another one, someone who's planning to go to Broadway.
James, minus 5 minutes left.
I'm done, really. Time flies. Okay. Well then, I'll show you one more taxi because that's fascinating. And we can have a look at an airport taxi that's also coming from an airport and showing a Broadway show. And let's find a more interesting one. We're getting the same recommendations, but yeah, I think you get the idea. They're relevant and they're generated by machine learning, and it scales beautifully. So now I can try and take some questions, or have I burned my whole time?
One question, the other questions over dinner. We first have another speaker. Could you start setting up, Jess? One question.
That's good, I think, because I stand between you and your dinner.
No, we have Jesse first.
Okay,
so we still have some time while he's setting up.
Cool.
No questions. You should definitely talk to the big data team.
I said it was a lively demo, but yeah, I think people had a beer and yeah. Okay.
Okay, then please a round of applause for James.